Welcome to today's session where we talk more about simple linear regression models. Here in this session, now what we've learned in our last session, just to give you a quick recap, and if you haven't watched that video, go ahead and watch that quickly. But just to give you a recap, simple linear regression, you have one independent, one dependent variable. We study the interactions. In our last lesson, we derived what do we really mean by these beta coefficients, how do we derive them, what is unbiasedness, the basic fundamentals. And now in this lesson, we go into the properties. These properties are essentially the applicative factors of econometrics, and you can really just apply them as soon as you understand what the properties are without needing to go through the entire process of deriving each value and going through the same shenanigans as we did in our first video. So this is really where we get into the practical things. Now over here, you realize that we are working through a bunch of ideas and topics. You've got properties of simple linear regression, you've got some theorems, you've got some concepts. We'll be focusing on the 5 properties and 2 theorems. Not all of them, but we'll get to them slowly. All right, let's get to it. Firstly, let's look at the properties of simple linear regression. What I've done over here is that I've created a quick cheat sheet. When I was going through the same concepts, when I was giving my exams or studying for them or doing my homework, it's really difficult for me to just recall and remember every concept that I was learning on a day-to-day basis and then applying it on a regular basis. So as you work through this, just take a screenshot. This will be your cheat sheet and you can use this for all the concepts associated with this. So let's look at all the properties. There are 5 properties in play. Number 1, linear in parameters. Number 2, random sampling. Number 3, variation in independent variables. Number 4, zero conditional mean. Number 5, homoscedasticity. The first 4 are pretty self-explanatory. The last one, they've tricked it up because, they can't give all the things so easy, right? So let's go through each of those properties. They're very simple. Number 1, linear parameters. In our last lesson, we learned about parameters and how to derive them. When we say linear parameters, we're essentially saying that the beta cannot be a beta square, a beta 1 to the power of 3, or square root of beta 5. Essentially, why we're saying that they're linear is because of the L in OLS, not the L that we all know what it stands for, but the linear in OLS. And when you have linear parameters, you can essentially define the relationship on a very linear scale. You can use non-linear independent variables such as x1 squared, or if you're looking at the relationship between page and age, you can use h square, h cube, h put to the power 4. However, your beta coefficients associated with each of those explanatory variables will always be linear in our OLS regression, which is random sampling. Now, this is not a property that will always be followed, but in general, it's important to understand the gist of it. Now, when we look at a large population of data, and we have to define the relationship between, let's say, wage and age, as mentioned previously, we look at the entire population, pick some random sample, and then we define the relationship. This is important because we want to create a pure relationship based on factors that are very independent to the nature. When you randomly select people or randomly select objects from a larger population sample, you collect characteristics and properties of every one, develop a regression, and without really explicitly mentioning those properties, you're able to run a regression together and identify them not directly as a part of your beta coefficients or independent variable, but maybe as your error term. And so that's why random sampling really helps us understand. Imagine you're looking at your class and you want to define how many hours of studies leads to higher level of grades in math. If you select only those students who've gotten 90% or higher, your results might be relatively biased or might not be completely representative of exactly the relationship between the number of hours studied versus the grades received. And hence you pick a random population. You take roll numbers 1, 5, 7, 15, 45. bring them together, and then understand them for yourself. That sample size will be too small, but you get the concept over here. Now, let's look at the third property, sample variation and independent variance. Let's say you want to take out a survey in which you talk about the relationship between the amount of hours studied and your SAT score. Now, the usual conviction that our parents have, let's say mom tells you, if you study more, you'll get better SAT scores. You want to prove your mom wrong, or in fact, get to know whether your mom is right or wrong. So you go to your class, take a survey of everyone, and you realize that there's a positive relationship between the amount of hours studied and the SAT score you get. You're like, all right, let's study. But if your intention is different, what you'll do is that you'll get the amount of hours studied to be equal to, let's say, 5 hours studied. Just that one group of people that only study 5 hours in the entire week. And then you realize that the SAT scores range from 1200 to 1400, and you do a regression on that. See, there the variable, the regression would not yield any usable values, because again you're using the same x variable and regressing it across all y values. So what we mean over here is that we need a little bit of spice, a little bit of variety in our x variable. And that's why you look at not just people who study 5 hours a week, but you also look at people who study 40 hours, also who did not study, who studied 20, who studied 30, and so on. So having that spice in x variable or the independent variable really gets you to the point where you're able to say, all right, if I study X amount of hours, or if I study X additional amount of hours, my SAT scores is likely to increase by a delta amount. Perfect. Now we look at the fourth property, zero conditional mean. What do we mean by zero conditional mean? Is that the mean of the error term given the independent variable should be equal to zero. In other words, the independent term should not impact the gross behavior of the dependent term. In other words, think about it the way we thought about in our graphs. The net mean of the error term is more or less zero because it cancels out and equals out. That's why you've got the OLS regression, right? But if we say that the mean given the value of x is not equal to zero, then you're talking about something different happening over there. That means that you're saying that maybe the value of the error term is somewhere dependent on x, or there is more to be captured in the data than it has been captured by purely the independent term. And that's where you go into multiple linear regression models. But if you have a non-zero conditional mean, then that leads you to a situation where your OLS regression no longer be valid. And hence it's important to check these things before you go into a regression. Last, homoscedasticity. This is an extremely important property. Homoscedasticity means that the variation in the error term is not a function of the independent term. So let's say we were talking about the wage and age regression. If we say that as the age increases from 50 to 60, the error term just blasts out of control and goes beyond imagination and just varies all across the board. And there's no real correlation no real relationship we can define over there. At that point, we start to think, is it really dependent upon, is it a true error term, or is it dependent upon the x? So when it is dependent upon the x, that's not an ideal situation to be in, and that could cause our OLS to be different or not accurate. Now, just to define what I'm saying over here, let's look at the graph over here. Onto your left, you've got heteroscedastic. Onto your right, you've got homoscedastic. You see how the variation between the dots and the potential line in the homoscedastic graph on the right is more or less fairly constant. If you draw the line connecting all the points together through an OLS regression, it'll be fairly flat. The dots will vary around the line. There won't be much variation. But if you look at the graph on the left, see, as your x-axis increases, the variation in those points increase. And when you have this situation, It leads to something called BLUE, which is Best Linear Unbiased Estimator. What is it? We'll talk about it later. But for now, understand the concept of homoscedasticity, and heteroscedasticity. Now, these are all the properties that we have for SLR. However, now their application comes in the form of understanding what is unbiased. Now, if you remember the last lesson, we talked about what is unbiased. Here's where we apply. Now, when you have properties 1 through 4, linear in parameters, random sampling, variation in independent, and zero conditional means satisfied, it means that your OLS estimators are unbiased. What do we mean by unbiased? When you say that your teacher is biased towards a certain student, you expect that student to get higher grades. Isn't that right? Yep. Similarly, when you say that an OLS estimator is biased, it means that the expected value of the coefficient, the beta coefficient, is going to be higher, lower, or something different. And so we need our OLS estimators to be unbiased because our expected value of those coefficients should always be the coefficient by themselves. And this is best explained by performing multiple regressions on different types of random data and eventually getting to the same value. So let's say you've got a million rows of data, all right, and then you break it down into 1,000 randomly selected rows times the total number of data sets that are created out of it. You run regression on each of those. Again, remember that this is randomly selected, so we're satisfying all the properties. The beta coefficients that will be found after each process, taking the average of each of them, will eventually lead to the beta coefficient found ideally that exists in that relationship. And that is the fundamental meaning of unbiasedness. This is theorem 2.1, unbiasedness of OLS estimators. And this is satisfied when MLR 1 through 4 are satisfied. Perfect. Moving on to the next part. Here's where we talk about goodness of fit. Goodness of fit is essentially when we try to understand how much of our independent variables are explaining the dependent variables. That's where the term explanatory or the explained variable come in. It's essentially the same thing as independent dependent variable respectively, but still it makes it a lot easier to understand this concept. Let's talk about R squared. R squared is a percentage value. It tells you it ranges between 0 and 1 in decimals, and then you convert it into percentage. And it tells you how good the model is based on the relationship defined. So your independent variable strongly defines the dependent variable, and hence your R square will be higher, which means that the range or the variation between your predicted values and the actual values is relatively low. And when you square it together, you get a very tightly packed OLS with the scatter plot. That is R squared. Remember that R squared does not tell you anything other than the pure goodness of fit. So when you're interpreting R squared in your exams, the professor asks you, what is R squared? What is the R squared of this regression? You say that the explained variable is explained by the explanatory variables at up to 35% of the sample cases, or 35% cases, or 35% of the explanatory value explained values can be explained using explanatory variables. The explained explanatory does get confusing, but essentially the concept is how much of your independent variables define the dependent variable. The value does not define whether a model is great, bad, good, or anything else. There's obviously a certain degree to which you'd want your R squared to be, but that's something that we'll cover later. It's called VIF. We'll talk about it later. Using the R squared, you come to something called SST, SSE, and SSR. You might be seeing on your screen. The term and the full term are strangely different concepts, and they don't even align in terms of the full form. Unfortunately, that is the case, and I asked my professor why that might be the case, but unfortunately, there's no answer for it. So, better learn it until you create your own term. So, first, let's talk about SST, sum or total sum of squares. In simple words, it is the sum of squares of the difference between the dependent value and the mean of the dependent value. The SSE is explained sum of squares, which is the difference between, which is the squared sum of the difference between the predicted y value or the predicted dependent value and the mean of the dependent value. SSR, which is the residual sum of squares, is essentially the sum of errors squared. Go back to what we studied. Error squared is essentially sum of the differences between y predicted and yi, the individual value. And that's how you get all these three. How are they important? We'll study about this more. But this is where theorem 2.3 comes in. We'll talk about this and the other associated concepts in our next video. Thank you so much for watching. Until next time. See you.